Hi, folks. Welcome back to part two. This is the points and lines section. We're going to go over the basic data analysis elements and ways in which networks are organized and the network data are stored. So let's jump right in. So we can define, networks are defined as the combined set of actors and their relations. And so actors are variously referred to as nodes, vertices, points, and relations are referred to as edges, arcs, lines, or ties. And this is just a simple little example here. I'm going to change our screen pointer here just to get some. Do this again. You can see that. So, for example, we have, okay, in this case, we have, actor B has a relation with actor A. So that's what these diagrams typically mean. We can have many different types of relations within this formalism, right? So you can have an undirected binary tie. So person C was in the same room as person D, and so that's just a line connects person C to person D. Instead, we might have a directed tie. So in this case, person C sends something to person D. So it might be an affirmation. So person C likes person D. Person D does not return the affirmation, right? So a directed tie goes from one person to another. Relations can also be valued. So it might be the case that instead of being in the same room as the other person, I've been in one meeting with, so person C has been in a room with person D once, person C has been in a room with person E 4 times, right? Because the relation been in a room with is necessarily symmetrical. If I've been in a room with you 4 times, you've necessarily been in a room with me 4 times, so there's no direction. Alternatively, we can imagine that B likes A a lot more than A likes B, or B sends money to person A at a greater rate or value than person A sends ties back. So this is the notion of value, and it's often a convention to represent a directed tie with a directed arrow, right? And the strength of that tie would be something like a value. In addition, we can have multiplex relations, which means we can layer over multiple types of relations. So it might be that I like you and I work with you or something. And so it's possible then that we can stack the same number of relations over the same set of nodes. And this is known as a multiplex relationship. And you can have as many of these as you want. So the ways in which we think then about the types of data are directed, valued, and binary, and then the type of relation that is there. And in most cases, I'm going to spend the examples I'm going to give are going to be directed binary graphs, but just know that unless I say otherwise, most of the time there's a rate that we can generalize these out to other types. Once you have these types of relations, we need to think about our level of analysis. And so in networks, the level of analysis is always a little bit tricky. The simplest level of analysis is the dyad at the very, very most level, but we tend to talk about ego networks. And that is we have a respondent and the people or relations they're connected to. That's the ego network. This may include, it's usually a one-step ego network, so it's ego and their direct ties. Every once in a while you can get two-step networks, but it's an egocentric network, so it's always focused on an individual. A partial network is the ego network and then something else around it, and this is a catch-all phrase for lots of different things. And a lot of your link tracing networks, for example, if I find a person who's tested positive for COVID and I trace that out a ways, I'll get a few steps. That won't be the global network. There'll be lots of missing links, but it'll be a partial network. It's just there for completeness. The biggest sort of distinction is between ego networks and global networks, or complete networks, or sometimes called sociocentric networks. These are networks where we have data on all actors for some relevant boundary. So this might be all kids in a school, or all judges in a district, or all senators in a Congress, right? So this is a way of, we have some boundary, and we're interested in focusing on the relations amongst people within that boundary. As you think about this, you can imagine defining them in various ways that they overlap, right? So this is just a graphical illustration of that same idea. So a dyad, or a best friend dyad, for example, might be the most local network you can imagine. And so I have one individual, they list their best friend, and that's what we have right here. An ego network would be that central person and the people they're directly tied to, right? It may or may not also include the ties amongst the people in the ego network. We could also then think about a primary group or a community that this person belongs to. So our red square there belongs to a community of people, a primary group. This is where most of their relationships happen, but they have one tie outside that group, right? Another tie that goes out here, another tie that goes out there. So a primary group or community is not necessarily bounded around a single individual. You can have ties that cross through that set. right? This is the two-step partial network where I've started with ego, gone out to their friends and friends of friends, and that gets me everyone else within 2 steps of the focal node. Notice that necessarily anytime you have an RDS or a link tracing design to generate a partial network, you're going to leave out the isolates and the isolated diehads. And so one of the main distinctions between a global network and a partial network, particularly these snowball kinds of designs, are that a global network, which include everybody in the network, often includes isolates or isolated diehads. And that's because you predefined the boundary as opposed to traced out from the relations. Now, social network data, then we have the direction and the value. We have the level, right, which is from that. The other element to think about network is what we call the modes of the data. And so a one mode data, or the a unipartite network, means that everyone's at risk to being tied to everyone else. And this is the most common friendship or sexual network data or contact data or social data. You're going to have something like friendship. This is just that slide we showed last time. This is in contrast to what we call two-mode data or bipartite data. In two-mode data, there's some partition of the nodes into classes such that people can only be connected between classes and not within classes. That's a complicated way to describe something that you bump into all the time. So something like being a member of a group or an author on a paper or words in sentences, right? So these are things that aren't directly connected to each other, but are only connected to each other through something else. So you're not connected to your co-authors by virtue of being friends with them. I hope you are, but it's not necessary. A co-authorship network is defined by the fact that you both are authors on a paper. And so what this looks like, and the reason it's called a two-mode network data, is that you can sort the data from one side to the next such that everybody on this side, in this case, women in a southern town, and events that they've attended, in this case, luncheons. And so we have Flora, Olivia, Catherine, and Helen, right? These folks all attended this particular event, and they're connected to each other through that event, but not directly connected to each other. And I bring these data up because this is by far the simplest data to collect. And so if you haven't collected data before on your own, give a thought to two-mode data, because often these data are already out there. If you have committee memberships, if you have activities that people are engaged in, like clubs and sports and so forth, or committee assignments in departments, or anything like this, jobs they've been in the past, it creates an implicit connection by virtue of their having shared these events. And so this is just a spatial layout of that. So just like we did with that high school network before, so see Charlotte is tied to these events, Brenda is tied to these events, and so forth. Now, one of the nice things that you can do with a bipartite or a two-mode network is you can create the projection of that network to get directly at shared events. So if I take the person projection of the persons through lunch networks, we can see that Olivia and Flora went to lunch together a lot. Flora and Sylvia went to lunch together every once in a while, but not as often as Sylvia and Helen, for example. And so this is the way to get a one-mode projection of who went to lunch with each other by virtue of by projecting them through the other mode. And this is the flip side of that, and this is why they call it a duality. We can simultaneously define this network not in terms of the people, but in terms of the lunches. So in this case, there's a set of lunches that had more people in common than the other set of lunches. And that shows you a social division in this little community. This is a very useful way to collect data. Just to give you an example that you might not, in the social networks and health realm, these are physicians that share patients, right? So physicians are not connected to each other directly. They're connected to each other by virtue of the fact that they both treated the same patient. Might be at different times, could be years apart in this case. But what we see, and this is in a single hospital hospital system in southeast Pennsylvania. And you see that within this one hospital, it breaks up into two separate communities. And what's interesting is that we found this was the case often in these within a particular hospital, based on electronic medical record data, that many hospitals would have multiple communities of physicians inside of them. Right? These are probably referral networks. And if you look at the readmission rates for each of these separate communities, you'd often see high variance. So within the same hospital, sometimes they perform about the same. You can see the difference between the blue and the red is almost nothing, but other times they perform radically differently. So if you get admitted to a hospital and you don't know whether you're in the high performing community or the low performing community, you might miss out as a health outcome. So this is one element of a health outcome that you might not expect otherwise. And what's fun about this is it's data that you didn't have to go in and survey physicians and say, which group do you belong to? Instead, by virtue of the fact that they have to bill for services, you can identify which physicians are engaged in which community. You can also think about networks, and I'm not going to spend any more time talking about this really today, but I just want to put it out there just to make sure you see it, is that in addition to one mode networks and two mode networks, and we can have these things that are called multi-layer networks. And multi-layer networks are really a mix of multi-mode networks and multiplex networks, in the sense that you can have different types of relations on different types of nodes, and you can combine them in one data structure. This is to matrices what tensors are, right? So that is, they're stacks of matrices, and just like TensorFlow allows you to think about new ways of analyzing data in a machine learning context from basic algebra types of ways. This is what multi-layer networks allows you to do, is that you can think about these things occurring in multiple settings. It's a really exciting new way of thinking about data, but we're not going to spend a whole lot of time thinking about it. I just want to point out to you that you will see this out there if you go out and read some of the literature. And basically what it is a way of taking otherwise like apples and oranges and putting them together in the same network in a smart way. And so it's a fun way to analyze these data. All right, pictures are fun. We all like pictures, but you can't analyze pictures. So let's start with the way the data are actually stored and organized. The traditional way to store network data is in an adjacency matrix. And an adjacency matrix is just a two-dimensional array with the nodes down the rows and across the columns. And the cell value here is the relation in question. So in this case, we can see we have an undirected binary network. We see that person A is connected to person B. And so in the row from A to B, we have an indicator saying that the relationship is on, so 0 or 1 in this case. And because it's a symmetric relation, B to A is also going to be the same. So this matrix you'll see is exactly symmetric. Now, if it's a directed tie, you do the same thing, but it's from and to, right? So here's a tie from person A to person B, and that's what we see here. We see a tie from person B to person A there. We see a tie from person C to person B there. We don't see any tie from person B to person C, so that tie is missing. So that's a directed adjacency matrix. A valued adjacency matrix, exactly the same. You just change the binary indicator with the value, and so it really is as simple as that. Now, the matrices are the best way to think about networks, because we can apply many of our linear algebra tools to the adjacency matrix and get smart things out of it. So if you know what you're doing, you can do things like, solve for the system of equations, find eigenvalues, and the rest of these types of things. And those end up being meaningful on the adjacency matrix. So you're going to see a lot of equations that we write using the adjacency matrix. An adjacency matrix is a good way to think about the data, but it's not necessarily the best way to store the data, just because an adjacency matrix ends up being pretty large because most people aren't tied to everyone else. So instead, we tend to store our data actually as either an adjacency list or an arc list. An adjacency list is what you would expect from a rectangular social science data set, right? So each row is a person, each column is a variable. The first column would be your first friend, and your second friend, and your third friend, and so forth. And so here we see the person C is tied to persons B, D, and E, right? Just like we would see here, so person C is tied to persons B, D, and E. An arc list, as an alternative, would be that you just list the present edges. So we have the tie between A and B, between B and A, between B and C, and so forth. And anything that's not listed there is assumed to be a 0, right? So it's a 0 tie. In these cases, it's a little bit important to make sure that you have some mechanism with these data structures to include your isolates. And so as an arc list, if you don't have a matching data set that includes all your node data, which you normally would, but just in case, make sure you do something like include a tie to yourself. So you'd have a tie from A to A if A were isolated, just otherwise the relationship would be lost. If you have a valued adjacency list, you need to somehow encode that information. And so in an adjacency list version, what you typically do is you have a corresponding relationship, a variable that is the weight. So I have my first friend's identity listed in this variable, and then I'd have the weight of that relationship listed in a corresponding variable. And the fact that friend 1 goes with value 1 and friend 2 goes with value 2 is implicit in your code book somewhere. Let's change out so I can get my pointer here. So then in an arc list, this is easier. Just for each relation, you can code as many characteristics of that relationship as you want as part of the data structure. It's really straightforward. For a 2-mode data set, where you have like persons and events, for example, it's the same thing as an adjacency matrix that we talked about before, except that instead of being a square matrix with the zeros down the diagonal, you have a rectangular data matrix. And so you have, for example, people down the rows and events across the columns. Then the trick you get to get the projection is matrix multiplication. So the adjacency matrix times its transpose will give you the person times the transpose times itself will give you the group matrix, for example. And this is a kind of a fun way to store the data. And again, you can also do this as an adjacency list or an adjacency or an arc list. It's just that the 2 modes are separated out that way. Okay. Let's start then. Those are the basic way data are sent. And the good news is most of the time, you don't have to think about these, right? These are held by the software program, but you're going to want to just know intuitively what they are. The best place to start, I think, with data analysis is usually going to be some sort of exploratory analysis, and visualization is a good way to get there. We're going to do a quick brief bit on visualization. I have a whole long thing I do on this. We don't have time to go through that in this particular setting, but just know that that there's a lot you can do with this, and I think it's worthwhile to spend a little bit of time thinking about it just to make sure you don't do something completely useless. The thing about the visualization tasks is that they tend to be the main reason to do it is to either communicate something to somebody else. So in this case, with the race high school friendship, we wanted to really be clear about what was there in terms of the ways in which these school networks were racially segregated, or just to intuitively do it for yourself, right? To build an intuition of your setting and the structure. So I really encourage you to spend, if you're going to do network analysis, I encourage you to spend a little bit of time just playing with your data and getting to know it. And visualization is a great way to do that. And the problem with visualization is that networks are relatively complex data objects. And consider these 4 visualizations. If I were to just hand them to you, you would probably walk away with 4 very different stories you want to tell about each of these settings. But if I set you down with a pen and paper and told you to trace out the relations by identities, you'd find quickly that these are actually the exact same underlying data. That is, these are just 4 different visualizations of the same network data. And this is the sort of the downside of network graphs. It's really easy to give yourself a misimpression if you don't know what's driving the underlying algorithm that gives rise to the image. So this is why I think it's really important to spend a little bit of time getting to know what some of these visualization things are. For the big picture problem, when you get to the point where you want to create visualizations for other people, you really need to, that is things that are not just for exploration, but are also for presentation. You want to spend a little time sort of balancing these 3 problems. And so there's some visualization strategy that we have, some algorithm for laying the points out. And that needs to map well onto the actual knowledge problem you're trying to solve. So what is it you're trying to understand? And that has to be accurate, right? And these 3 things have to go together. And it turns out that there is never a perfect fit for all 3 of them simultaneously. And so you have to make some choice to find a way to balance one against the other. And you're going to perhaps take a cost to data fidelity in order to better solve the problem, or you might have to switch your strategy up a little bit and use a slightly different algorithm in order to be a little bit more to one than the other. And this is just something you need to do. This is part of the art and craft of networks as opposed to on the science side of it. All right. So let's start with the basic network heuristics. Since network visualization is generated to build intuition, you need to understand how these things are generated under the hood. And there tends to be these 2 different types of relations or of layouts. The tree-based layout starts by reserving one dimension of the layout space for hierarchy, right, for the flow of goods. So in this case, we have a root, right? And this tree goes from the root to 2 branches and it continues down, and the hierarchy is very clear. So the vertical axis has a meaning. It goes from root to leaf, right? The other type of algorithm that we typically see as opposed to a tree-based layout or a hierarchical layout is called a force layout or a space-based layout. And here the goal, again, is not that X and Y mean something in particular, but that each relation is given about the same distance. And so we see that person 1 and person 2 are the same distance as person 2 and person 3 from each other. So each relation has the same distance. And that allows you to see how nodes are close to each other. Now for a hierarchical network, so these data are an organizational chart, say, this kind of a force-directed layout doesn't do a very good job. If you look really, really carefully, you'll see that here is the node that has a root that has only ties going out and none going in. And so I can reconstruct the hierarchy by chasing out from the root, but you shouldn't have to work that hard to see what's there. On the other hand, if you imagine doing a hierarchical layout on data that isn't necessarily hierarchical, I can say, oh, this node's at the top, but it's completely arbitrary, it's meaningless. And so in this case, a space-based layout is going to give rise and help us see these three clusters in the data in the way that a hierarchical layout wouldn't. So the two most common, I think, by far layout traditions in network analysis are the hierarchical layout used for hierarchies and organizational trees or decisions and flow diagrams in these force-directed or space-based layouts. A third type of layout that is used a little more frequently nowadays is a fixed coordinate layout system. There are two types of fixed coordinate systems. The obvious one are maps. So if your underlying data are some kind of geographic map, then it might make sense, given your knowledge problem, to use that map as your underlying space. So in this case, this is that physician data I told you about a little bit before. These are actually hospitals. So we have a hospital here is exchanging, in probably Spokane is exchanging with a hospital in Missoula or something, or one in Seattle. And so there's Denver and so forth. And that's nice, right? As a reader, I can look at this map because I know what the map is, and I can use that intuitive knowledge to help me understand how relations are mapping onto this. Whereas the version on the right here is the exact same data, but I'm using a space-based layout. And so you can see that this black cluster here is this cluster. So Chicago is kind of the central place in the hospital exchange network, and it's bridging LA, Texas. I'm just moving my eyes back and forth here to look at the colors, right? And so you can imagine what that is, but it doesn't really do a good job in the same way of intuitively helping you see what's there. Now, I've added something here you're going to notice in the rest of the visualization slides is this fit statistics. What the fit statistic is the correlation between the distance between the points in the screen and the number of hops I would have to take through the network to link those two nodes together. And so a good space-based fit should have a high correlation. And so I should be able to correlate the screen distance with the social distance should be really high. And so this fits better, right? So this network is a better mathematical fit to the distance distribution in the data, but it doesn't provide the same intuition. Now the cost, of course, to a graph using a map is the problem with any map layout, which is that the west or part of the United States is very sparsely populated. And so this looks like a much weaker set of connectivities than you see on the eastern half of the United States. And so you have to figure out, well, what problem are you trying to solve? If it's to explain to people something that where the geography would be useful, then that distortion is worth buying. Otherwise, this might be better. The other fixed layout that people use sometimes are circle graphs. And a circle graph is useful because the one thing a circle does is it makes it possible to see when lines a line will never be exactly over another line. That's rarely useful for graphs of any size. One thing that I have found circle layouts to be useful for is when I combine a circle layout with a space-based layout. And so in this case, I've found some communities in the network, and there's an underlying topology to that network that I then put into these circles to identify the communities. And so there are cases where that might be a useful thing to do, but generally the circle is often an option in the software, but often not that useful. Chord diagrams are common and popular now because ggplot spits them out pretty easily, and they are kind of network data that give you a connection from one side of the graph to the other. These are circle plots, and I think they're useless, frankly. They're the pie graph of of networks, and I recommend avoiding them. You could display these data so much better as a space-based network as opposed to a circle. And the issue, of course, is that the circle, because it has no underlying inherent meaning doesn't carry any knowledge that people can use to help build intuition. Now, one thing you need to get used to with network layouts are distorting the underlying data. And this is the kind of thing that you just wouldn't do with a scatter plot, right? But it's pretty common to be done with the network data because you're dealing with a heuristic to start. That is, there is no right display of network data. There's just a better display versus a worse display. And so if you have a problem that you need to solve by virtue of your display, it's often useful to go in and do a little bit of distortion in order to make that problem clear, because what you're doing is you're trading one heuristic off against another. And so that none of these heuristics are sacred. So you just want to make sure you pick one that is meaningful. And if it is some sort of distortion, you want to be clear what that distortion is. So for example, in a clustered network such as this, you might want to highlight the clusters a little bit to make it clear of the ways in which the intercluster ties differ from the intra-cluster ties. So we can do that by just shrinking the clusters. And so these are the exact same figures, except in this case, I've shrunk each cluster and made it clear where the links between clusters come from as opposed to the links within clusters. Another way in which you can get some of these kinds of distortions is that you might spread out or apply a fisheye lens to one area that's really densely packed in order to make it easier to see what's going on inside of it. So in this case, I've put a little fisheye over here on this dense cluster to move it a little bit. Now you'll notice that this has come at a cost to fit, right? In both cases, by doing this kind of distribution, this distortion, I've cut the link a little bit between the screen distance and the physical distance, but I've done that deliberately. And while it comes at a fit cost, yeah, I think in this particular case, it created a little bit more clarity for a particular knowledge problem. And this is why I say you always go back to that same question between trading off the knowledge problem you're trying to answer against the layout method and the data fidelity. Many software tools will give these curved edges. They tend not to do much. In Gephi, they do provide a sense of direction, but for a large graph, that's not visible. So I recommend against it. It's pretty, but it doesn't provide any information. You want to be a little bit careful with really, really dense networks. So this is the co-voting network of the 109th Senate. And what you see is that there's a clique of Republicans and a clique of Democrats, and they tend to vote with each other a lot. A few people are voting cross-party. That doesn't happen as much anymore. But really, you're not getting a whole lot out of the image itself as a network. You'd be better off in this case to use a heat map of the adjacency matrix, which is a better way to visualize something like this. You can actually then see which are the senators in this case that are voting across a little bit better. Sometimes it's useful to abstract from the network entirely. So if you're looking at spread through a network, you might be better looking at a diffusion curve rather than the underlying network. And this is what we've done here. It's a very large dynamic network. And instead of giving us the this big ugly network, a hairball that we couldn't look at, what we really wanted to see was if you were to start a diffusion process from a series of different nodes, what's the population of diffusion curve is going to look like? You can see most of the time you're going to end up in this region. A few times it'll take a long time before it ultimately reaches everyone else. And so again, if it's possible to do a little bit of work there, this collection of curves does a better job of explaining the problem than the underlying graph itself might have. On the other hand, you might say, let's just look at the actual diffusion tree. This is an example of trying to figure out the ways in which concurrency would promote the spread of a bug through a network. And it turns out there are two kinds of concurrency. There's networks that where the relationships overlap in time a little bit, but they're still easy to order from an earlier relationship to a later relationship, and that's because one clearly comes before the other. They're just sort of in parallel but overlapping times. You can imagine other cases where one relationship is embedded in the other, and that creates what we call a backwards concurrency. It moves the other direction. And in this case, we were able to see, if you look at each of these diffusion trees, you can see that there are cases where there's often one of these dark red, these backwards concurrency ties. And we can ask ourselves, well, in which case was the tree itself, would it not have continued on had it not been for the concurrency? And you can recolor it that way by by asking for each relation, is there an upstream backwards concurrency? And that sort of really makes clear that in order to get these big chains, you have to have backwards concurrency. And this is part of the argument we were making about the ways in which concurrency matters for the flow of goods through networks. You can layer more information, and so this is that same tree where we've now added in the race of the nodes and the other ties where relationships didn't happen, and that's a nice way to sort of get a little more information on. Now, as networks become dynamic, it gets to be a little bit harder to see what's there. Animation can help with that. Now, that's what we've done here. This is timing on that adolescent sexual relationship network I showed you before, just the largest connected set of it. And as the relationships came on, these are week panels. So 1 week is each time clique is a week in time, 7 days. And so you can see then that these relationships come on and they're ongoing at a given time, and then they fade off and they die. Now at the end here, you're going to see them all die at once. That's truncation. That's not, they didn't all break up after prom or something silly like that. But this is, the animation is a nice way to get an intuition about the ways in which these relationships go. You can do the same thing with waves of data, right? So here is the Colorado Springs drug data. And if you layer them over time, you can see time 1, time 2, 3, 4, and 5. And it's just a nice way to look at the way in which these things are going back and forth like that. Okay. If you have lots of time where things move through panels in time, it might be a good idea to stack them. This is one of the first examples of a multi-layer network, and that's what we have here. And it's you see each layer of the network and people moving through each of those layers. You can collect them into panels like these. These are, I think these are actually baboons. And so you can see the ways in which the baboons are moving through time. In this case where they're all connected at one wave, and then at this fourth wave, they start to split into 2 groups. We're going to shift now from doing visualization to thinking now a little bit more about calculating metrics on the network. Metrics has probably been the single most common way of doing network analysis for years, up until the most recent sort of move towards statistical models of networks. And it's really important to get a good sense of what these metrics do and how we understand them. Now, there's an entire universe of metrics that we could go through, and so we don't have time to do them all. We're just going to touch on a few of them that are really sort of key to understanding the basic topology of networks. And so I've picked a handful here that I think are worthwhile to go through in a little bit of detail, and that'll give you a sense of everything else you can do. The main sort of big picture take home you should take from these is that there are lots of ways to measure networks and measure properties of networks. And you should, as a theorist and an analyst, sort of free yourself from some notion that there's only one way to do this, right? There are lots of ways to do it, and you should find a measure on a network that captures a social feature that you care about the most. And there are lots of these, right? And so if you have a theory about the way something flows through the network, then there are ways that we can capture the features of the network that relate to flow. On the other hand, if you really think that segmentation matters for some kind of competitive process or something, then there are measures of segmentation that we can deal with. And oftentimes, they're the things that you're going to create yourself. And so I really want to give you the pieces so that you can then think a little bit more about how you might create a measure that matters for you the most. So we're going to go through 4 classes of measures for the rest of these, this part of the presentation. Basic volume are just sort of the foundation basic elements. These will go quick. Reachability and paths are what make network systems, and there are lots of different versions of this. We're going to focus on the simplest. Centrality is an entire universe of centrality scores. We're going to go through a handful of those to give you a sense. Centrality fundamentally is trying to figure out why a node might be important. And it turns out that importance in the network is fundamentally linked to the ways in which you think the network matters. So this is why there are so many different centrality measures. Then we're going to touch briefly on community detection, because oftentimes, especially in modern network analysis, your network is too big to deal with just on its own. And so we need to segment it. We need to identify smaller subsets that we can play with and make sense of. And community detection is the way to do that. All right, let's get started. The first one then, I'll get this to work here. Set up our pointer. So the main way of thinking about volume in the network has tended to be this notion of density. So density is the traditional measure of how many ties there are in a network relative to the number of possible ties. So if you think about what this is just the average of your adjacency matrix. So if we're going back to our figure here, our little basic toy network. If you have a valued network, then density is literally just the sum of the network divided by the number of possible ties. Now, most of the time, the diagonal of the network is useless for us. And so we exclude that. So this is why it's n times n minus 1 because we don't care about the diagonal. And so there are 24 possible ties. I'm sorry, the sum of this particular matrix is 24. There are 20 cells where that could happen, so the average value of the matrix is 1.2. You only get a density greater than 1 when you have a valued network. If we're binary, as we've seen below, we see that 50% of the possible ties are present, and so that's density. Density is a little bit problematic. It's traditional, that's why I included here, but it's problematic because in most sparse networks, the number of possible ties goes up with the square of the population size, whereas the sum of the matrix goes up linearly. So for really big networks, you always get really small density. So it doesn't really tell you what you think it might tell you. A better measure is usually the average of the degree. Degree is the sum of ties to or from each person. So if your network is directed, then we distinguish in degree from out degree. So in degree is the number of ties a person receives, out degree is the number of ties they send, and so we can just take the sum of those, right? So the sum across the rows is your out degree. This person sends 1 tie and receives 1 tie. This person sends 3 ties and receives 1 tie, right? And notice, of course, that the sum of the in degree is equal to the sum of the out degree because you're just summing the same information in 2 different directions. So that always has to be true. Again, if you have a value tie, you can do the same thing. So it's in that technical terms, it's the weight of each edge as opposed to the degree, but it's the same idea. So you just sum across the rows or sum across the columns. Now, once we get beyond the simple volume, the number of ties you send or receive, we can think about what makes a network a system, and that has to do with the connectivity of the network. And in connectivity, we tend to think about 3 elements of connectivity. Reachability, is it possible given the pattern of edges in the relationship for one person to reach another? Distance, that is how far you have to travel in a network to connect 2 people. And redundancy, how many different ways is it possible to move from one direction to the next? We're going to go through each of those in turn. So reachability is just a binary indicator. Is it possible to go from one node to the other? And that's only possible if there's a path connecting them. So we can see here that A can reach persons B, C, and D, right? So we can go from A to B to C to E, right, and so forth. A path in a network is a directed sequence of ties from one node to another. And so you can go from A to B to C to D. And it doesn't go backwards and it never repeats. A walk is any sequence of nodes or edges. It can go anywhere you want. So a walk is just randomly moving around the network. A cycle is a path that starts and ends on the same nodes from A to B to C and back to A again, for example. Reachability is the condition upon which you can trace a path from one node to another node. So if I can trace a path of whatever length one node to another, then it's possible for them to be reached. We call that a connected component. The maximal size of the maximal set of nodes for which it's possible for any one to reach any other one is called a component, and that's the largest component. So for example, going back to our little example we had before about romantic relations in Jefferson High, we can see that this large section of 288 nodes is a component. Each person can reach everyone else. These other pieces are also components, right? So we have a bunch of small components and one big component. If your network is directed, then we distinguish strong components from weak components. A strong component is any set in the network where it's possible to reach each person to and from every other person. So in this red case, for example, you'll see that each node can reach every other node and be reached by every other node in the red set. Same thing in the blue set. So here we can go this way and back around. Because these are cycles, even though you have an asymmetric tie here, A reaches B, and B can't reach A on that edge, but B can reach A by going around the circle, right? So these end up being strong components. And the notion of a strong component is if you respect the direction, then it's still possible for whatever's there to circulate. And so if I were to drop a secret into this network, we'd see that this person would tell it to that person, who would tell it to this person, and they would learn later that that secret was told to everyone in their group. A weak component is any path that you could trace through the network, ignoring the direction of ties. And so if it's possible for one person to reach another, irrespective of the direction of ties, then it's a weak component. Now, it's kind of interesting because a connectivity has a strong link with this notion of degree. And so many real life networks have a very skewed degree distribution. That is, most people have 1 or 2 ties, but a few people have really, really, really large numbers of ties. In fact, this is typically displayed, the number is so high that we typically log it and look at the log of degree. And what makes what's known as a scale-free degree distribution is that you have a linear distribution in the log-log scale. And when you see this kind of degree distribution, what that's really telling you is that you have a handful of people that are way out here in the tail of the degree distribution. Now, why we talk about that here is that this is also, it tends to be linked to this notion of connectivity. Is if you have a few high degree nodes, then they often end up being the nodes that uniquely connect the network. So in this case, there's a small number of nodes, the yellow nodes, that if you remove them would disconnect everyone else in the network. And so the tail of the degree distribution, these nodes on the tail tend also to be hubs. And if they're hubs, then if you connect them, they disconnect the network. Let's give you an empirical example. This is Colorado Springs Sexual Networks. This is a network of commercial sex workers and their johns. And so you can see then that there are a few nodes that are really have a high number of ties. And if you remove them, you would end up perhaps disconnecting the overall network. Okay. Now, there's a big debate about scale-free networks. I'm not going to go through this debate. Most real-life networks do have a highly skewed degree distribution, whether or not it's literally scale-free, that is, whether or not it fits this exact functional form, that the probability of observing a node with degree k is equal to k to some exponent, whether or not it fits a perfect line is debatable, and it's not worth us going into, quite frankly. All right, so if we know that a node is reachable, then the question is, how hard is it to reach them? And the ease with which we reach other nodes is governed, at least not inconsequentially, by the distance between nodes. And the traditional version of distance is geodesic distance. It's the shortest number of hops I need to get from one node to the next. And you are familiar with this intuitively if you think about 6 degrees of separation or something like that. But we can imagine node A here. Node A is connected to a handful of nodes, 4 nodes in 1 step, a few more nodes in 2 steps, in 3 steps, 4 steps, and 5 steps. So node A is 5 steps from this node out here. Notice that there are a handful of these edges that I didn't highlight. That's because these nodes are sort of radial nodes within the same distance from A. So they're not part of the geodesic path from node A to one of these others. Now you can do this as both weighted or unweighted, so it's perfectly reasonable to do it on a weighted graph, and you can do it on directed or undirected graphs. So if it's a directed graph and it's impossible to reach somebody, then we say it's a missing value or it's an infinite distance, right? So node A can't reach node G, and so we say there's no finite distance between node A and node G. Again, just looking at this one, you can see that the average number, the longest path in the Colorado Springs Sexual Network is 17 steps from this node way out here to this node, right? And so it would take a long time for that to go. On average, each person is within 3 steps of 75 other people in the network. The two parameters that people tend to measure in terms of distance is the diameter of the graph, like what is the longest path, and the average path length. What's the average number of steps you need to go from one to the next. In real networks, we're often interested not just in the likelihood that a person can reach someone and the diameter, but we're interested in what features close the network on itself. And this has to do with redundancy. And so that's the third measure of connectivity we want to think about. And so if we think about these notions of paths again, I can go A to B to C to D. I can move through these steps, right? But it's pretty hard to imagine something getting transmitted across a single edge. It's much more likely to get transmitted if there are loops that you can have alternative paths for. And so redundancy provides these alternative routes through the network. We can think about redundancy either globally or locally. Local redundancy is also known as transitivity, and it's the extent to which a friend of a friend is also a friend. And so if you can imagine these closed triads, those have really high local redundancy. And local redundancy is interesting for us from a diffusion standpoint because it creates this local sort of cluster, and things have a hard time getting out of that cluster. They don't spread out to the rest of the network very widely. Global cohesion, global redundancy, is the extent to which the network as a whole is reconnected by multiple paths. And we like to think of this with this notion of structural connectivity or structural cohesion. And it's the minimum number of actors that, if removed, would disconnect the graph. So in this case, these little 4 examples are a way to illustrate this. On the far left here, you have a network that is disconnected, so it's impossible for anyone from the top We see at the bottom, as we move over, this network is one connected. There's a single node that if I removed it would disconnect the graph. This network is bi-connected. That is, there are two nodes that if I remove it would disconnect the graph. And this node is three connected. There are three routes that I can get to it. And you can see how this works, right? That if I were to remove these red nodes, it would disconnect the graph. There's an interesting equality that has to do with node connectivity, which is that the number of nodes required to disconnect the graph is also equal to the number of node independent paths who could link the graph together. And so it's the case that in this network, there's only one path that would need link a node from the top to the node to the bottom. In this case, there's always at least two paths that only fall through the source and target node. In this case, there are three. And that equality is a nice feature because it links the ability to segment the network with the ability to spread something through the network. One interesting thing about cohesion, structural cohesion, is that it creates this nested set of more redundant nodes, or it's often the case that that's the feature within networks. And so, for example, this entire network is zero connected, right? So the connectivity is equal to zero, and that's because these two nodes are isolated and these things are connected. But then if we go a little bit further, we can see that we have two connected components, an isolated dyad and this larger one. Within the isolated dyad, we have a set that are one connected, two connected, and three connected. And so this is what's known as a cohesive blocking, and we expect that the nodes that are more deeply nested in the overall network are more likely to share things, right? And so that if this were diseases flowing through the network, then if you're jointly connected to somebody of high redundancy, then you likely have the same diseases they do. Whereas if it's a secret or a knowledge of the universe that's sort of going on in this community, the nodes that are deeply embedded in the network should know more about what's going on there. So distance and connectivity features are the parts of the network that tell us something about how the system as a whole is connected. If we want to shift perspectives a little bit and locate a node within the network, then we need to focus on how a node is situated in the network. And centrality is the main way of doing this. And so centrality is a broad class of measures designed to distinguish a node from the center to the edge on some version of a connectivity score. Now, the reason I say some version of is that there are lots and lots of different centrality measures depending on what feature of the network you're trying to emphasize. Okay? But for now, it's useful to think of this as a location measure. It locates nodes relative to each other on how deeply embedded they are in the network. Now, it turns out that there are lots and lots of different measures. In fact, there's a fun little piece that Scotch put together that gives you the periodic table of centrality. There are hundreds of centrality scores, like literally hundreds of centrality scores. We're not going to go through even a moment of all of them. Instead, I want to focus on four classes of measures. Degree we've already talked about, but I'll just reintroduce it in the same framework so we can be on the same page. Then I'm going to talk about closeness, betweenness, and eigenvector centrality measures. I think combined, these four measures give a really nice overview of the ways in which centrality can be thought of and help you build your own measures. All right. So starting with degree centrality, we can imagine that degree centrality is just the number of people you're tied to. So in this case, the central node is tied to 7 other people. Each people on the end are tied to 1 other person. In this case, you notice this little kite graph, each person has 3 ties, except for these people in the end that have 2. In the ring, each person has 2 ties. In a degree centrality measure, you got to remember that degree is an entirely local measure. So this person right here has degree 2, and it's the same as this person that has degree 2. This person has degree 3, and so does this person, and so does that person. Even though intuitively we would expect them to be relatively different. Our intuition says this person is more central than this person, even though from a degree centrality measure they're the same. And that's because degree is entirely local. I just want to keep that in mind. Just to really drive that home, our intuition would be that this person would be somehow the most important node in this network. It's connecting everyone else in this set, but it has the lowest degree centrality, and that's because of, again, the degree centrality is just capturing this pure local measure. Now, centrality is a score that captures an individual's position in the network. We're often interested in also characterizing the distribution of centrality across the entire network. And we do that with things that are called centralization scores. So centrality is an individual score, centralization is a graph score. Centralization is the traditional measure, and it takes the observed score, we subtract from that, the maximum score, we subtract the observed score from that, right? And we do that for all pairs of nodes in the network, and then we normalize it by some feature that makes sure it ranges between 0 and 1. This is known as Freeman centralization. It's a standard traditional measure that's been used, and it's you can use it if you want. I tend to think that it's really hard to interpret because the scale of this correction measure tends to not be intuitive for lots of folks. So instead, you can also, if you'd rather, just use something like the variance, right? And so, because these are really the same, right? So this is, we've subtracted from a maximum. You could, in fact, instead pick a different constant, in this case, the mean, and that just gives you the variance. And so again, the whole point is that the centralization talks about the variance in centrality. The reason that's important is that for certain classes of network, we know what that variance has to be. So if you have a star network, then the variance has to be maximal. And so that's what the Freeman segregation index is trying to do. You can't get any more variance in the centrality of a network score than you would see in a star network. Similarly, if you have a circle network, it has to be completely equal. Everyone has to be the same. There's everybody in this because everyone's structurally equivalent. So everyone has the same pattern of ties. They're indistinguishable. So in that case, the variance is going to be 0. Freeman segregation is going to be 0. Freeman segregation is defined such that when you're at maximum variance, you're also going to be Freeman segregation of 1. That's how it's defined. In this case, you'll notice the Freeman segregation is really close to 0, right? And even though there's some clear structural differentiation in this network, and that's again because we're looking at degree centrality, which is a local measure. So everyone has effectively the same degree here. Similarly on the line graph. Now, degree centrality isn't very interesting most of the time. There are a few health processes where you could imagine where degree centrality might matter. But for most things, we care about centrality because it allows us to figure out how far somebody is from something else or some other kind of system set. So that's so we can take this notion of distance that we defined on the graph as a whole, and we were talking about reachability, and map that onto individuals to get how far they are on average from everyone else. And that gives you closeness centrality. So closeness centrality is the distance between each pair of nodes in the network, and we invert it, right? So that's classic distance or closeness centrality. And so you can think of, imagine the farness of somebody is how much the distance is just summed up across all pairs. By inverting it, you get closeness. And again, on our little example networks, the first person is directly adjacent to every other person, so they're going to be as close to everyone else as they can. If you think about the distance matrix, person 1 here is 1 step from everyone else. Everyone else in the network is 2 steps from each other because they have to go through the middle person to get there, right? So the closeness centrality is just going to be the sum of this inverted, and that gives you these scores, and then we normalize it by something. That's what this last column is. You can't see because my mug's in the way. All right, so that's the normalized score. The normalized score is chosen to fit between 0 and 1, and it works well for something like a star graph because the central person will always be there. In a circle graph, each person is 1 step from 2 people, they're 2 steps from 2 people, 3 steps from 3 people, and so forth. And so it gives you this exactly equal set, and that will always be the case in the circle. Whatever centrality score you always have maximum variability in a star graph and minimum variability in a circle graph. A line graph, you start to see a little bit of the substantive difference you would expect, right? So the people at the end have the lowest centrality because they're far from everybody. As you get towards the middle, this person has to go the fewest steps to reach everyone else. So they're closer on average than everyone else. Again, we see that here. This person in the middle now has the highest centrality score because they're the fewest number of hops from everyone else in the network. The third model of centrality we're using is called betweenness centrality. Betweenness centrality counts the number of times a node is on a path between 2 other nodes, is on the shortest path between 2 other nodes. So in this case, you can imagine that A is between H and D because H has to go through A in order to get to D. And in fact, in the star graph, everybody has to go through the hub to get to everybody else. And so that's what defines betweenness. Betweenness is your ability to block the flow in the network because you sit on the path between one node and another. So we define it that way. So we imagine the geodesic between nodes J and K. Is node I on that path? If so, you sum that up for all nodes J and K, divided by the number of paths that link nodes J and K. It's usually normalized by this funky function here, which is the number of possible shortest paths between two nodes. We don't really care about that for the moment. And again, you see about what you'd expect, right? So in the graph, in the star graph, the people on the edges are going to have centrality of 0. The person at the 1 is going to be centrality of 1. And this is because if you're at the end, nobody has to go through you to get to anybody else, right? You're either going to be a source or a destination. In this little kite network, we find that the node in the middle is the most central because anybody on the leaf to reach anybody other leaf has to go through the hub there to get to them. And so that creates this bottleneck, which means they have a really high centrality. It's not perfect centrality because there are these paths within each leaf that this person doesn't sit on, but otherwise they're connected. Again, the circle is going to be your most even set. Betweenness centrality can be a little bit tricky, right? Imagine I've made up a graph that have this particular characteristic, which is that the node that looks like it's in the middle has the lowest betweenness centrality or close to the lowest betweenness centrality. And that's because of the extra redundancy in this network means that any node can find a way around this node to get back to them. So there aren't that many geodesics, many shortest paths that have to pass through this node in the middle, which means that their betweenness centrality is going to be relatively low. This is just to highlight this notion that what makes a centrality score valuable depends on what the underlying flow feature is. Betweenness centrality matters because you think that a node is central, and it's important because it's on the shortest path connecting two others. If there's some other thing that matters, then you want to capture a different kind of location measure, a different sort of path measure. So it turns out then that the reason we focus on these three, degree, closeness, and betweenness, I'm going to set aside for a minute the eigenvector and power centrality. I'll come back to that. If you think about them, I like to start with them because they're sort of the foundational measures of centrality. And in combination, they tell you a lot about the network as a whole, right? So degree is basic volume, closeness is how many hops you have to go to reach somebody, betweenness is your ability to bridge some other people. So if you imagine a node that has low degree but high betweenness, that means that that node doesn't have many ties, but they're crucial for connecting otherwise disconnected parts of the network. On the other hand, if I have low degree and low betweenness, this means that egress connections are redundant, right? That there's lots of other routes that go around the node. And so the combination of betweenness scores do a really nice job of situating where a node sits in the network. So what I encourage you to do is that if you have a social process, say a diffusion process or a search process or an exposure process that you think is operating in your setting, then think about how you would operationalize that flow process on the graph, and you can probably find a measure that maps on that directly. One of the interesting versions of this are a whole class of measures known as eigenvector centrality measures. And the version that I like is called Bonasich's power centrality. You can use plain, it's not that different than plain eigenvector centrality, which I'll come back to in a minute. But the reason that I like Bonasich's power centrality is somewhat historical. Phil Bonasich invented this measure, a long time ago to think about social exchange networks. But the main thing that Bonasich's centrality does is it says that the centrality of any given actor is a function of these two parameters, a scaling factor that we're just going to set aside, doesn't really matter for us, and a power function. And this is a weight that you give to the network that says how local, it's the radius of power. And what I mean by power in this case is that the centrality for one node is equal to their number of people they're tied to, like degree centrality, weighted by how central those people themselves are. Intuitively, what this means is that I'm more powerful if I'm tied to otherwise powerful people. And I'm not as powerful if I'm connected to a lot of powerless people. And so it's an interesting idea, right? So it's one thing to be king of the kings as opposed to king of the non-cans, right? And so it does a really nice job of capturing that element. And so if the beta coefficient is set really high, it's the maximum is the size of the largest I vector. If it's set really high, then is the case that essentially I'm saying that I'm going to calculate this centrality score over the entire range of the graph. If it's set low, then I'm only going to look at it, it's going to essentially become degree centrality. To give you a sense of what this looks like, again, part of the reason I like the Bonasich version of this as opposed to the base version is that this beta coefficient can be signed. It can be either positive or negative. And so if it's positive, then you really have just a radius on classic eigenvector centrality. It means that I'm more central, the more central people I'm connected to. If it's negative, then I get higher centrality if I'm connected to otherwise disconnected people. All right, so it sort of moves you between, it interpolates between what betweenness centrality does and what the closeness centrality does. It does a nice job of doing that. To give you a sense of what this value is equal to, so for this line graph up here, the bonus that we've picked a beta value of 0.23. If I set it positive, you'd see that the central person is going to have the highest centrality, right? If I set it's negative, then the people who have the most centrality are actually these two nodes on the penultimate, the ones that are almost on the end. And that's because they're uniquely controlling these people on the outside. It's kind of a cute little feature. All right. The reason that you might care about Bonasich power centrality is because it is this, it has this feature that you're more powerful the more connected you are to other powerful people. The other thing is this is also the centrality score that underlies PageRank. Right, so PageRank is a version of eigenvector centrality, and you care about PageRank because you probably used it today. It's what Google uses, or a variant of PageRank. Is how Google determines whether or not a search result is a valuable one or not, is do other things point to it. So the original version of PageRank was just the centrality of a single node. The importance of that node in web search was a function of the number of other websites that pointed to that. Now, they've gotten a little more sophisticated since, but that's the basic idea. And from a social standpoint, it allows us to distinguish nodes that not are just high degree, but they're high degree and connected to important other people. All right, the third element then that I want to spend a little bit of time talking about in terms of basic metrics are community detection. And this is sort of moving up. So we've talked first at the global network with reachability and connectivity. Then we went to the local network, or the local sort of level, to talk about centrality and how nodes are linked to each other directly through the network and where they are situated in that set. The meso level between those two are communities. And communities are subgroups in a network that have lots of ties to each other relative to their ties to people outside the group. And so this little made-up network here, you have these different groups. I've colored them and clustered them so you can see them. We often want to find them. We want to have tools that let us go in and find the communities in the network. And this is actually a pretty hard thing to do. There's a lot of different ways of doing it. If there are hundreds of centrality measures, it turns out there are probably also hundreds of community detection measures. We're not going to talk through them all, of course, but I want to give you a little bit of a sense of the flavor of the ways these things work. Broadly, there are two ways you can go about finding communities and networks. The one is you can use hard-coded graph theoretic models. And so you can think about cliques, K-cores, K-flexes. These are mathematically defined patterns of ties. So for example, if I think about a clique means that each person is tied to every other person in the network. And intuitively, that's what a group is. The density is perfect. Everyone is tied to at least n-1 alters. Every pair is connected by only one step, right? So the distance is short. Each of these are things that you might think about features that define a group. The alternative way to do it is to think about algorithmic methods. That is, we don't want to identify a strict measure of a clique because if I'm missing a single edge from a clique, it's no longer a clique. And it wouldn't count as a group. Instead, we want an approximation to clique. And so there are lots of different things that do that. We're going to talk about some variants of those in a moment. These kind of graph theoretic determinations that we have, the beauty of them is that they're really clear and you can define them exactly. The problem with them is that they're very fragile. That any change in the graph structure is going to make it not fit the definition. All right, so if you delete a single edge, it's no longer a clique. The other thing about cliques in particular is that they heavily overlap in practice. So I've circled all the cliques here. So nodes 6, 7, 5, and 4 are in a clique, but 5 and 4 share a clique with nodes 1, 2, sorry, 3, 9, and 8. And so the heavily overlapping nature of cliques makes them fairly difficult to use in practice. K-cores are defined as nodes that share at least K ties with every other node in a group, right? So in this case, A is a pink node. All these nodes have at least 3 ties to every other node in the network. If you were to just add a single line between A and B, the entire thing would become a K-core of the same size. So they're very fragile, and it's true for lots and lots of these. We could go through a whole bunch of them. And so in practice, particularly if graphs are, except for some very specific circumstances, we tend not to use these kinds of measures. Instead, we tend to focus on these heuristic measures. And so the heuristic measure says, well, none of these specific measures of cliquedness or groupedness are sufficient in and of themselves to define a distinct group. But we might be able to define something like the odds that you and I are friends with each other. And if we can maximize the subset of nodes that are likely to be friends with each other, then that would give us a good enough measure of cliquedness. In order to do this, we typically have an algorithmic sort procedure. And you start by taking your entire population of grants, and you have some process that allows you to say these 2 nodes get put in group A, these 2 nodes get group B, and you do that over and over again until you find a process that fits. And so we have to, in order to get that, it's this 2-step process. First, you have to define relatively well your measure of fit. That is, what determines a group, and there has to be some way that you can scale that, right? So it has to be a continuous measure so you can search over it. Then you have to have some heuristic, some sorting process that lets you get from a collection of nodes spread across the entire set to the grouping you want to get. And that's a non-trivial task. It turns out that over the years, a very nice measure of fit that we've come up with is this thing called the modularity statistic, or the quality function Q. And modularity is nice because it has a very simple way of thinking about it. You imagine the different parts of this. I'm going to go through this here. Let's just walk through what this formula does for us. So it starts by saying, let's take our observed ties. So the A is the adjacency matrix. We have a tie between I and J. We're going to subtract from that some function that tells us the expected number of ties between I and J. And in this particular example, the expected number of ties is called a degree model. So degree is K. And so the probability that I is going to connect to J is just the number of ties that I sends times the number of ties that J sends divided by the number of possible ties that they could send. Right? This is the classic chi-square set. And so this is the observed value. This is the expected value. We subtract one from the other, right? Governed by a resolution parameter we're going to come back to. Ignore that for a minute. If they're in the same group, we add to the quality function. If they're not, they don't. So what's nice about this function then is that we're summing up the number of times we find people who are in the same group of each other above and beyond what we'd expect by random chance. And that's the fundamental quality that we care about, is do we find more ties within groups than we would expect by chance? And that's what this normalizing concept is. Intuitively then, this measure ranges between 0 and 1. If it were 1, that would mean you never find a tie across as groups. If it's 0, then you find as many ties across groups as you'd expect by chance. That means that this thing is essentially goes to 0. To give you a sense of what this feels like in a couple of small graphs, I just made up these examples. So here's a little 6-node, 6-group network where I've set Q to be really low, so about 0.2, and you can tell you can't really see any groupedness to it. This is a heat map of the mixing matrix. And you find a little bit of value here in the diagonal, but not much. Q goes to 0.5. We can start to see a pretty good strong set of groups. 0.7 here almost, get a really strong cliquedness. You only get a Q of 1 if you have completely separated cliques. You'll get a Q of 0 if you have a random graph. There's no structure at all. All right, I'm going to back up just a little bit. No, never mind. We'll go back. Where am I at here? Yeah. All right, so a couple of things to think about with this. process that I'm giving you here is to say that once I know an assignment of nodes to groups, I can evaluate this function. What we want to do is flip this around and use this as the parameter we're trying to maximize as we search over possible solutions to the assignment problem of putting nodes into clusters. And so the solution problem here is, are nodes I and J in the same group or not? That's going to be a sort and an algorithmic problem. Now, it turns out that there are lots of different ways to do this, right? So we can find different kinds of solution processes for this. The solution that I like, the algorithm that I like in terms of the off-the-shelf versions, if you're not going to write your own, is the Louvain method by Blundell et al. And this is an agglomerative clustering procedure that starts with a set of nodes that everyone's in their own nodes, and then slowly adds them together to the extent that it improves fit. The second version that I really like is called edge betweenness. And edge betweenness is a divisive model. And it says, imagine the entire network. Let's split that network where it maximizes the modularity for two groups. Then for each of those groups, let's split it again. It's not exactly what it does. There's some details under the hood, but intuitively, that's kind of what it does. It's a really good model. It will provide a maximum modularity score, but it's really slow. Right? So it only works well for really small networks. Now, a third version that I'm not going to go through in detail here, but it might be worth just mentioning. For those that are familiar with singular value decomposition or SVD methods, such as factor analysis or its variants, you can run a simple latent factor model on a distance matrix and get a not awful fit for assignment of nodes to clusters. That is, if you treat people like items in a scaling matrix and you treat the distance matrix as inverted created closeness matrix, it starts to look a lot like a covariance matrix. And if you hold your nose and squint, you'll get something and just run a latent factor analysis on a distance matrix. You will get an SVD solution or something like an SVD solution for the assignment of nodes to classes. It's not a great model because it doesn't do any checks for connectivity, so because you're really just hijacking a different kind of process. But as a first cut, particularly on very big networks, it works pretty well. So a couple things to keep in mind. When you do a cluster analysis of this type, you're always going to find clusters, so they will always be there. So if I give you a random network and tell you to find it, the modularity score won't be high, but you will almost always, by random chance, have something better than zero. And so a cluster algorithm will find clusters. It doesn't necessarily mean those clusters exist in the real world. The second thing is, because these are heuristics, and we're using heuristic tools to sort nodes from all in their separate groups to communities, they will differ, right? So if you run the same algorithm twice on the same network, a little bit of random noise can create different solutions. And if you run different solutions, different heuristic algorithms on the same data, you'll often get different solutions. And this is just an example of that. Here I've taken 3 different algorithms that are off the shelf and applied them to the same underlying data, just to help you see that you often get slightly different solutions. So the NegaPi is an old style social network analysis group finding tool. And you'll see that it differs from the recursive neighborhood means solution, which is a version I came up with a while ago, in that my solution puts these into one group, this one does not. It splits F and E here into 2 different clusters than I do. And so this is something to keep in mind. If you end up running, if you have a small network and you really care about the assignments in a particular school or in a particular setting where the details of being assigned to one group or another are really going to matter, then it's probably worth your time to run a bunch of different algorithms at different features and see how well they correspond. Because if you get radically different solutions from one algorithm to another, then you're probably picking up on a lot of noise. On the other hand, if you have largely consistent solutions, then that's a better evidence that you have the right solution. In fact, one of my favorite algorithmic solutions to the clustering problem is called consensus clustering, where you go through and you weight each edge by the number of times a different algorithm jointly assigns those nodes to being in the same group. And so that's a really nice way of saying, throwing up your hands if you don't know the best algorithm to use, just use them all and take the average effectively. But just be aware that that's going to be the case, that you're going to get a little bit of differences on the edge depending on which group assignment algorithm you use. Now, most of the time, people are using clustering algorithms like this, community detection routines, because they're trying to take a really big data set and turn it into something that's manageable, in which case you might not care if one node gets assigned a little different in one algorithm than another, so long as the big macro clustering is relatively consistent and it provides you with a solution that is manageable, right, that you can do something with when you're there. So just a word of caution. Now, I want to return now to that pesky resolution parameter. One of the things that people liked about modularity when it first came out is that because it ranged between 0 and 1 and had a feature where if you only had one cluster, it had to go to 0, it would provide a natural way to optimize. And you might assume that if I can optimize, then the algorithm itself will tell me the number of clusters that's in my graph. I don't have to decide that a priori. It turns out that's only true if you, for any given fixed value of this resolution parameter. If you change this resolution parameter, then that's going to change the relative weight of the expected versus the observed part of the Q formula, and that's going to change the number of groups you find. If you set your resolution value really high, that means that I'm going to find a large number of relatively small groups. If I set my resolution value low, I'll typically find a small number of really big groups. And so what the resolution parameter ends up being is that it was a hidden parameter that governs the number of groups and the size of those groups you're going to find in the data. And so this ends up being a fundamental problem of real data for networks, is that the number of clusters in the data really depends on what scale you're willing to look at. So if I want to look at really, really detailed close bits, then I'm going to find lots of little clusters. If I sort of step back and want to look big, then I might divide the world into Democrats and Republicans, and I won't know much about the internal divisions in that set. But the way you focus, like the scale you focus on, that is a choice that you're going to make. It's not given a priori by the data. There are some settings that have a really key structure to them, and any algorithm was going to converge on that set. But in reality, most of the time, that's not the case. And so instead, what you have to do is search over your resolution parameter. And so this is an example from a paper that nicely sort of shows how these resolution parameter varies. You could start with a resolution parameter close to 0, and I think this is rescaled, this is actually 1. And if you search over a bunch of small values of this, you'll get a small number of clusters. If you search over a lot of big features, you'll get even a lot of little clusters. But notice that there are lots of different solutions that you can get depending on which resolution value you pick. Now, one of the nice things about this particular graph in this example is that oftentimes if you search for lots of different values of your resolution parameter, you'll find these plateaus. And these are spots where for that given scale, the solution tends to be relatively consistent. And that's a good indicator. Here's another example. Peter Muka has a nice, and colleagues have a nice post-processing feature that they go through, and that allows you to search over a whole bunch of different resolution parameters and identify the relatively small number of solutions that stabilize on a particular number of clusters. In fact, what they discovered is that there's this manifold of all possible solutions defined by modularity. Because of this difference, you're essentially defining a line. That modularity, this coefficient, defines a line in this space, and there is this manifold which nicely defines the optimal level of the solution that you can get. And you go through and calculate a bunch of, and you can now do this relatively quickly, calculate a bunch of communities on your data, array them by the resolution value and the modularity score. You can identify empirically what this curve looks like, and you can cross-classify that with the stability in terms of the number of groups and identify these points where you get relatively strong solutions. And that's what we encourage people to do. This is feasible when you have one moderately sized graph, tens of thousands, maybe hundreds of thousands, that kind of scale. If you have many, many graphs over many, many scales, it does get to be somewhat problematic. But again, it's just to point out that it's really hard to get away from this choice of the scaling parameter. And lest to think that this is not a networks problem. Of course, this is true in any feature. So the rule of thumb to pick a number of factors in a factor analysis with eigenvector value or eigenvalues greater than 1, that's the same thing as a resolution parameter. That's an arbitrary choice to some degree. And to the extent to which you make that choice arbitrary, you still have to make the choice. It's not just by default. Okay. All right, so all of these are inductive procedures. I think that I want to be really clear that that's the case, right? So it is possible to propose a deductive solution. So it could be the case that I know already that there are two groups in this network, and I want to identify the optimal set of two groups. And so that's fine. You can fit that. You can also imagine that I have some feature like race or grade or age or something like this that I think sorts my network into one side or the next. That then would be a function of a feature of the network. And I want to ask how well does that feature divide us into the two groups? And that's known as an exponential random graph model, in fact, and we're going to talk about those in a minute. So there are ways in which you can do this. There's also ways you can say, let's move away from a hard coding entirely and go for a soft embedding in a space, like a latent space model. And that's possible as well, and we'll talk about those. But just keep in mind that this is a nice way of exploring your data. And because I can't resist, there's one more element I want to talk about, and this is this notion of roles. And so community detection is one class of trying to identify nodes that have more ties with each other than they do with anyone else. Another way of thinking about the community detection is role detection. And so role detection is the positional analog to community detection. And role detection, instead of trying to find sets of nodes that have the most ties with each other, you want to find sets of nodes that are structurally the most similar to each other. So two nodes are considered to be in the same role as opposed to the same community if their pattern of ties across lots of different relationships are similar to each other. And you can see that really clearly in our little toy example we started with at the start of this little lecture set. Is that parents and children differ in the way in which they are arrayed across these different kinds of roles. And that's how you find roles. It's exactly like community detection, but instead of looking at the direct time matrix, you look at a role similarity matrix. That is, in order to block model, you identify some definition of equivalence. Structural equivalence is the one I'm sort of providing with you intuitively right now, but I'm not going to go into the details of that today. You measure the extent to which degrees of actors are similar across that measure of similarity, of relational similarity, and then you cluster on that. You develop a representation and you assess the adequacy. This ends up being just community detection on a role similarity matrix. And this is what that looks like, right? So for example, if I were to imagine through the three adjacency matrices that are defined in this little toy example we've been playing with, we have a romance relationship, we have a feeding relationship, and we have a bickering relationship. And we see that our nodes 1 and 2 are our parents, nodes 3, 4, and 5 are our children, and children do not share romance with anyone in the network. Parents share romance with each other. The feeding network goes from the parents to the children. The bicker network happens amongst the children. I'm missing a tie there. And we get this similarity score by just taking the network and stacking it. For a directed relationship, we stack both the observed version and its transpose, because we want not only who do you provide this for, but who provides it for you. And then we say for each pair of nodes, calculate how similar they are. And so we see that person 1 and person 2 match 100% of the time on these features, right? So they have the exact same set of ties to and from, and they're exactly different with everyone else. And so the similarity network ends up being the same for both of these. And that's all you've done. So this ends up being a really easy clustering problem because I have two completely disjoint cliques. But in real world data, of course, you're going to have something a little different than that. But that's just, I wanted to throw that out there as an intuitive way to deal with multiple relational networks. If you want to induce roles, it's just community detection on a similarity matrix as opposed to a direct time matrix. All right, we've gone through a lot of things in this section. These are the ways that we describe networks. We're going to shift gears now and talk about models for networks, particularly the ways in which we model diffusion and statistically model networks themselves. So I'm going to close this out. Hope everyone gets a chance to take a break, and we'll come back in a moment.